A decoder is a combinational circuit that takes a small number of binary inputs and activates one or a predefined group of many output lines. Think of it as a mail sorting machine. The address binary code tells the machine which mailbox output line should get the letter. The standard symbol shows several input lines on the left, a block labeled decoder, and many output lines on the right, often with an optional enable pin. An encoder does the opposite. It looks at many input lines and produces a binary code representing the active input. Imagine a crowd voting system where each voter has a unique button. The system reads which button is pressed and outputs a short binary number that tells which voter spoke. The standard symbol has many inputs, an encoder block, and a few outputs, sometimes also an enable. Functional difference: decoder equals 1 of n to n, select one output. Encoder equals n to 1 of m, compress many possible inputs into a few bits. Decoders are used for selection, address translation, and demultiplexing. Encoders are used for priority detection, digitizing analog selections, and compact representation of signals. Both devices may have active high or active low outputs, and they can be built with NAND, NOR, or AND/OR gates depending on the logic family. Symbolic notation: decoder d sub n to 2 to the n, or simply n to 2 to the n decoder. Encoder e sub 2 to the n to n, or 2 to the n to n encoder. They may also include an enable pin, shown as a triangle pointing to the block. Explanation: to build a truth table, list every possible combination of input bits, and write the required output pattern. For an n to 2 to the n decoder, inputs a sub n-1 a 0. Outputs y0 y sub 2 to the n-1. Rule: y sub k equals 1 only when the binary value of the inputs equals k. All other y are 0. Example: 2 to 4 decoder n equals 2. 0 0 0 0 0 1. 0 1 0 0 1 0. 1 0 0 1 0 0. 1 1 1 0 0 0. From the table, derive Boolean expressions using minterms, product terms, where the output is 1. y0 equals not a 1 and not a 0. y1 equals not a 1 and a 0. y2 equals a 1 and not a 0. y3 equals a 1 and a 0. These are already minimal because each output is a single minterm. For a 2 to the n to n encoder, the reverse. Inputs I sub 2 to the n-1 I0. Only one should be high at a time. Outputs b sub n-1 B0. Rule: output bits are the binary index of the active input. Example: 4 to 2 encoder, inputs I3 to I0. 0 0 0 1 0 0. 0 0 1 0 0 1. 0 1 0 0 1 0. 1 0 0 0 1 1. From the table, Boolean expressions are derived by grouping rows where each output is 1. B1 equals I2 or I3. B0 equals I1 or I3. These are minimal sum of products forms. The systematic design of a standard n to 2 to the power n decoder follows 3 steps. Identify inputs and outputs. For an n-input decoder, we need 2 to the power n outputs. Label inputs a sub n-1 to a sub 0, and outputs y0 to y2 to the power n-1. Write minterm equations. Each output y underscore k is true only when the binary representation of k matches the inputs. Y underscore k equals, and from I equals 0 to n-1 of a sub I to the power b sub I. Where b sub I is the ith bit of k, use a sub I if b sub I equals 1, otherwise not a sub I. Implement with gates, use an AND gate for each minterm and an optional enable, and gate that gates all outputs. Example: 3 to 8 decoder. Inputs a 2, a 1, a 0. Outputs y0 to y7. Minterms: y sub 0 equals not a sub 2 and not a sub 1 and not a sub 0. Y sub 1 equals not a sub 2 and not a sub 1 and a sub 0. Y sub 7 equals a sub 2 and a sub 1 and a sub 0. Gate level 8, 3 input and gates, each fed the appropriate true or complemented input. If an enable en is required, place a 2 input and before each output. Y underscore k equals en times minterm underscore k. 4 to 16 decoder follows the same pattern, but uses 16 4 input and gates. In practice, CMOS libraries provide a decoder macro that internally uses a tree of NAND gates to save area. Explanation: a priority encoder not only compresses many inputs to a binary code, it also decides which input wins when more than one is active. Think of it as a fire alarm system: the highest floor alarm should be reported first because it may indicate a more serious situation. 4 to 2 priority encoder with enable. 0001 enable 1 output 00 valid 1. 0010 enable 1 output 01 valid 1. 0100 enable 1 output 10 valid 1. 1000 enable 1 output 11 valid 1. 0110 enable 1 output 10 because I2 wins valid 1. 0000 enable 1 no output valid 0. Any inputs enable 0 disabled output valid 0. Logic derivation assuming I3 is highest priority. B1 equals I2 plus I3. B0 equals I1 plus I3. Valid output V equals enable times I0 plus I1 plus I2 plus I3. Tiebreaker: if I3 equals 1. Other terms are ignored because the equations already give the highest code. 8 to 3 priority encoder. Inputs I7 down to I0. Priority I7 greater than I6 greater than I0. B2 equals I4 plus I5 plus I6 plus I7. B1 equals I2 plus I3 plus I6 plus I7. B0 equals I1 plus I3 plus I5 plus I7. Enable gates the three expressions. Bi equals enable times expression I. Valid flag V equals enable times I0 plus I7. Tiebreaker logic: the sum of products already resolves ties because the higher order inputs appear in more terms. For example, I7 appears in every output equation. If a design wants to force a specific output when multiple bits are high, a small mask circuit can be added. Explanation: Karnaugh maps, K-maps, provide a visual way to minimize the logic for both decoders and encoders by grouping adjacent ones or zeros for POS. The goal is to reduce the number of literals and gate levels. Example: minimizing a 3 to 8 decoder with enable. Without enable, each output is a 3 literal minterm. If we add an enable n, the expression becomes y sub k equals n times minterm sub k. Using a k-map with n as an additional variable, we can see that n appears in every product term, so it can be factored out, yielding a single AND gate per output plus 1 extra AND for n. The final implementation therefore uses 8 3 input ands fed by n. Example: reducing a 4 to 2 encoder, non-priority. Assume inputs I3 to I0, only one active at a time. Initial sum of products. B1 equals I2 plus I3. B0 equals I1 plus I3. A k-map for B1, variables I3, I2, groups the two ones directly, giving the same expression, no further reduction. However, if we add a don't care condition for the case of all inputs low, we can treat those cells as ones and sometimes eliminate a gate. For instance, adding a term not I0 to B0 may allow the expression B0 equals I1 plus I3 plus not I0, which can be implemented with a 2-input OR and a NOT, depending on library costs. Boolean algebra shortcuts. Factoring a B plus a C equals a open bracket B plus C close bracket. This is useful when an enable line multiplies many terms. Consensus theorem. A B plus not a C plus BC equals a B plus not a C. It removes redundant product terms. De Morgan converts AND of OR to NOR NAND gates, often yielding a gate-level reduction. Using these algebraic identities together with K-maps yields the smallest possible gate count for a given technology. Explanation: timing in decoder/encoder circuits is critical because many downstream blocks, counters, memory bus arbiters rely on clean, predictable signal edges. Propagation delay ties sub p. Defined as the time from a change on any input to the final stable change on an output. For a typical n to 2 to the n decoder built with an enable AND followed by an n input, and the worst case delay is T sub p max equals Tn plus T and n. where Tn is the delay of the enable gate and T and N is the delay of an N input, and often implemented as a cascade of two input gates, adding open parenthesis n-1 close parenthesis times T gate. Example 3 to 8 decoder using two input NAND gates, each NAND delay equals 2 nanoseconds. The 3-input AND is made from two NANDs. First NAND combines two inputs, second NAND adds the third. Total delay approximately 2 nanoseconds. First NAND plus 2 nanoseconds second NAND equals 4 nanoseconds. Setup and hold for sequential interfaces. When the decoder output feeds a flip-flop, the flip-flop setup time T setup and hold time T hold must be satisfied. T sub P max less than or equal to T clock minus T setup. T sub P min greater than or equal to T hold, where T clock is the clock period. Hazards. Static 1 hazard : output should stay 1 but briefly glitches to 0 during a transition of inputs. Static 0 hazard : output should stay 0 but glitches to 1. In decoders, hazards arise when two minterms share a common input transition. Overlapping product terms can eliminate them. Elimination technique: add consensus terms or use two-level NAND implementation, which is hazard-free for some of products. Practical tip: after minimization, simulate with a timing tool, for example ModelSim, and inspect waveforms for spikes. If hazards appear, insert extra gating or use a latch-based design for critical signals. Memory address decoding. When a CPU wants to access a specific memory block, the address lines are fed into a decoder that activates a chip select line. Example: 16 kilobyte memory divided into four 4 kilobyte chips. 14 address bits are needed. 2 to the power of 14 equals 16 kilobytes. The two most significant bits, a 13 and a 12, are inputs to a 2 to 4 decoder producing chip select 0 to chip select 3. Only the selected chip sees enable equal to 1. This reduces wiring. Instead of 14 separate enable lines, only 2 decoder inputs are used. BCD to 7 segment display driver. A binary-coded decimal digit, 4 bits, must illuminate the appropriate segments. A to G. The circuit is a 4 to 7 decoder with some outputs inverted. Common anode versus common cathode. Truth table maps each BCD code 0000 to 1001 to a 7-bit pattern. Codes 1010 to 1111 are treated as blank. All segments off, they become don't care terms that can be minimized. Using K-maps, each segment line is expressed as a minimized sum of products. Often a combination of NAND and NOR gates yields a compact driver. Code conversion circuits. Gray to binary encoder. Gray code has only 1-bit change between successive numbers. A 4-bit gray to binary converter uses a priority encoder with feedback. B3 equals G3, B2 equals B3 exclusive or G2, B1 equals B2 exclusive or G1, B0 equals B1 exclusive or G0. Access 3 to BCD. Access 3 adds 3 to the normal BCD value. Subtracting 3 is done by a 4 to 4 decoder that adds a negative constant. The resulting logic can be implemented with a few exclusive ORs and AND gates. These conversion circuits are essentially small encoders that translate one coded representation into another, useful in digital clocks, calculators, and communication interfaces. Question 1. 3 to 8 decoder design. Design a 3 to 8 decoder with active high enable N. Provide the Boolean equations, a gate-level schematic, and calculate the worst-case propagation delay if each 2-input NAND gate has a delay of 1.5 nanoseconds. A solution sketch. Minterms: y0 equals n not a 2 not a 1 not a 0. y7 equals n a 2 a 1 a 0. Implement each 4-input and using 3 2-input NANDs, NAND structure. Each NAND adds 1.5 nanoseconds, so per output delay equals 3 times 1.5 equals 4.5 nanoseconds. The enable N is fed into the first NAND of each line, adding no extra stage. Hence TP max equals 4.5 nanoseconds. Question 2. 4 to 2 priority encoder. Given inputs I3 to I0 with I3 highest priority, write the minimized output equations and draw the logic diagram including an enable N. Verify that when I2 equals 1 and I1 equals 1 and N equals 1, the output corresponds to I2. A solution sketch. Equations derived earlier. B1 equals Ni2 plus I3, B0 equals Ni1 plus I3. Diagram 2 input OR gates feeding the outputs, each OR also ended with N. Test case I3 equals 0, I2 equals 1, I1 equals 1, I0 equals 0. B1 equals N open 1 plus 0 close equals 1, B0 equals N open 1 plus 0 close equals 1, which gives binary 1 1 equals 3, which is the index of I2 binary 1 0. Actually, priority encoder returns the index of the highest active. I2 gives 1 0. Since both I2 and I1 are high, priority gives I2 1 0. Our equations produce 1 1, so we must add a tiebreaker. Modify B0 equals N open I1 and not I2 plus I3 close. The corrected expression eliminates the hazard, demonstrating the need for an extra term. Question 3, BCD to 7 segment. Create the minimized Boolean expression for segment a top horizontal of a common cathode 7-segment display using a 4-bit BCD input D3 to D0. Show the K-map and the final expression. A solution sketch. Truth table for segment A, on for digits 0, 2, 3, 5, 6, 7, 8, 9. Mark 1s for those BCD codes. Treat 1010 to 1111 as don't care. K-map grouping yields. A equals not D3 not D2 not D1 plus not D3 D2 not D0 plus D3 not D2 D1 plus D3 D2 not D1. Simplify using algebra 2. A equals not D3 not D2 not D1 plus not D3 D2 not D0 plus D3 not D2 D1 plus D3 D2 not D1. Implement with 2 3-input NANDs and 1 2-input NAND. Total gate count equals 3. These worked examples illustrate the systematic approach expected in exams.